We're going to go over derivatives of inverse trig functions and the integrals that yield inverse trig functions, starting with derivatives. There are 6 formulas that we learned in AB, but really there's 3 of them, and they come in pairs. Right, the derivative inverse sine and derivative inverse cosine are the same, except opposite each other. It's important that you memorize the rules, okay, and we can use product rule, quotient rule, or chain rule as needed when we're taking the derivatives of these functions. Chain rule would come in especially when I have something besides a plain old x in any of these spots. Okay, so definitely watch out for chain rule when you have something besides a plain old x in any of those spots. When you do have something besides a plain old x in any of those spots, then you match that in terms of what's being squared over here. Okay, so whatever, or what's in the absolute value. So these things have to always match each other. Okay, and then if it was a composite, then I would just multiply by the derivative of whatever was inside the function. Okay, let's look at some examples. Let's do some examples. Okay, I have inverse cosine of x cubed. I want to take the derivative. Okay, the derivative for inverse cosine is -1 over square root of 1 minus whatever is inside that function, quantity squared, times the derivative of the inside. Okay, so I'm going to have -1 over square root of 1 minus x cubed, quantity squared, times the derivative of x cubed, which is a 3x squared. Simplify it, I get -3x squared over the square root of 1 minus x to the 6th, and there's my answer. Here's number 2, okay, x squared times inverse tangent of e to the x. Okay, now for this I'm going to need chain rule because I've got something besides a plain old x inside my trig function, but also product rule because I've got an x squared times inverse tangent. Okay, so let's start with product rule. So my derivative, f prime, is going to be first x squared times the derivative of the second. And derivative inverse tangent of something is 1 over 1 plus whatever it is squared times the derivative of whatever it is. Okay, so I'm going to do 1 over 1 plus, I have an e to the x in the inside of that inverse tangent, so I'm going to have e to the x quantity squared times the derivative of e to the x, which is also e to the x. Okay, and that's first times the derivative of the second, now plus the second times the derivative of the first, and the derivative of x squared is 2x. Okay, let me clean this up because it's a mess right now. Okay, I can make this first part all one fraction, or I can keep it in as a product of two things. I'm just going to make it all one fraction as an x squared e to the x over 1 plus, and e to the x quantity squared, I multiply the exponents, I get e to the 2x. Okay, plus 2x, I'm going to bring that 2x in front of the trig function, times inverse tangent of e to the x. And that's my answer. A little messy, but let's look at this one. G of x is 2 inverse secant of square root x. When I go to take the derivative, that 2 is just a coefficient, so it's just going to hang out front. The form for inverse secant is 1 over the absolute value of whatever's inside that trig function times the square root of whatever's inside squared minus 1. Okay, and we're going to have a square root x inside those absolute values and a square root x quantity squared in there, and times the derivative of square root x, which is 1 over 2 square root x. Okay, cleaning this up, I've got a 2 out front, and 2 out front and a 2 in the denominator, which are going to divide out, and I'm left with a 1 up top, a square root x times a square root x, which is just going to give me an x. Okay, I'm going to keep that x in absolute values because I want to make sure that it's a positive x value, because if I have square root x, which is positive, times another square root x, which is positive, I'm going to get a positive value there, times the square root of, and I'm going to have an x minus 1 in here. Okay, there's my answer. I think given what we talked about in AB, and just these 3 quick refreshers, you should be good on taking your derivatives of your inverse trig functions. Let's talk about our antiderivative rules that yield inverse trig. Okay, the antiderivative rules come from the derivative rules. So we have the integral of 1 over square root of 1 minus x squared dx giving us inverse sine of x plus c. The integral of 1 over 1 plus x squared dx giving us inverse tangent x plus c. And the integral of 1 over absolute value of x times square root of x squared minus 1 dx giving us inverse secant x plus c. I want you to notice that there are only 3 formulas here. The reason there aren't 6 formulas is that we can't have a different answer just because there's a negative involved, because we can pull negatives out of an integral because of our coefficient rules, of coefficient properties of integrals. Okay, so if I have a negative inside my integral, I can pull that negative outside the integral, and then I just have negative inverse sine x. There is no integral that yields us inverse cosine x. Okay, so there are really just strictly 3 formulas in here that we're going to worry about, okay? We generalize these antiderivative rules, and these are the rules that you would see in your textbook because of variety, okay? So we don't necessarily need to have just a 1 minus an x squared inside that square root, or an x squared plus 1 in our denominator, or an x squared minus a 1 in the denominator for this, in the case of this last problem here. So if we have any quantity squared there, we can have these various formulas here. Okay, so a can be any number, and we just want to make sure that when we're looking at this setup that we realize that it's a difference of squares in the case of the formula that yields us inverse sine or inverse secant, and a sum of squares in the formula that gives us inverse tangent. And it's important to try to set up our integrals as either the difference of squares or the sum of squares, so we can recognize what what's standing in for our x and for our a. The other really important thing to watch out for is that if there's anything besides a plain old x squared in your integrals, you're going to need a u substitution. Okay, so let's look at some examples now. Let's start with a real simple one. I've got the integral of 4 over square root of 1 minus x squared dx. Okay, that 4 is just a coefficient. The square root of 1 minus x squared, just to kind of do this without an inverse trig approach, but just if I were given this integral, I notice that I have a composite function. I notice that it's a quotient, neither of which I can integrate without some work. Okay, this function cannot, this integral cannot be simplified. So if I try to do a traditional u sub on this, and I let u be the inside of the composite, my du is a negative 2x dx, and I do not have that for my u substitution, so it does not work. Okay. So I need some other means, and that's when a u substitution fails you on something like this, that you should think, hey, maybe it's an inverse trig problem. So let's try inverse trig setup. So if I look back at my forms that I was using before, I notice that this is the general form that gives me inverse sine, and the 4 on top is just a coefficient, so I hold the 4 as a coefficient. The integral of 1 over square root of 1 minus x squared is inverse sine x, and I need a constant of integration, and there's my answer. Let's look at another. Let's do the integral of 1 over 9 plus x squared. Again, if I try to normal u sub and let u equal the denominator, the inside of the composite, u equals 9 plus x squared, my du would have an x in it. I don't have another x for my du. So I'm going to realize this is an inverse tangent form. I have something besides a 1 here, so I'm going to want to write it as the sum of squares. Okay, so I have 1 over 3 squared plus x squared. Okay, and if you look, that's our form for inverse tangent, and the antiderivative of 1 over a squared plus x squared is 1 over a inverse tangent x over a, so I'm going to do 1 over 3 inverse tangent of x over 3 plus c. Okay, let's look at the next one. Okay, so I want to give you guys an example of a situation where a traditional u substitution will work. So let's go ahead and do this one. It is a composite, it is a quotient. I can't simplify the composite, so if I try u sub on this one and I let u be the inside of the composite, then my du is a negative 8x dx. And I have an x dx, so I can work with this. So I have a negative 1/8 du equals x dx. Okay, so I'm going to have negative 1/8 the integral of, I have square root of u in my denominator, and my x dx is my negative 1/8 du, and I need a 1 for a placeholder. Okay, so now I have negative 1/8 times the integral of u to the negative 1/2 du, which I'm going to hold that coefficient, increase the exponent by 1, I'll get u to the positive 1/2, divide by 1/2 or times 2, and that gives me a negative 1/4. I'm going to plug back in for u, and I have square root of 1 minus 4x squared, and I need a plus c. Okay, so here's a situation that I don't want you to think every time you have a square root in the denominator or any time you have one of these quotients that looks similar that it's an inverse trig problem. Sometimes it is a simple u substitution. Okay, here's a very similar problem, the integral of 8 over square root of 1 minus 4x squared, and the denominator is exactly the same. If I try the exact same u substitution, it'll fail me because I don't have an x in my numerator. All right, so I'm going to have to look at this as an inverse trig problem. All right, it's important for that denominator that you see it as the difference of squares, especially if you have something besides a plain old x squared over here. Right now I have a 4x squared, so I have 8 over the square root of, I'm going to write it as the difference of squares. I have a 1 squared minus, what do I square to get 4x squared? I have to square 2x. Okay, and then whatever's in there, in here, is going to be my u for my u substitution. Okay, so when it's something besides a plain old x squared, like I said in the beginning, you're going to need a u substitution. The u would be the inside of that composite right there. The u would be 2x. Du would be 2dx. Okay, I don't have a 2dx, but I have an 8dx, so I'm going to multiply both sides by 4. Okay, all right, so what does that take me to? I have the integral of, I have square root of 1 minus u squared. That's in my denominator. My 8dx is going to be a 4 du. I need a 1 as a placeholder. All right, and this is my form for inverse sine. So I have 4 inverse sine u. Plug back in for u, and I get 4 inverse sine of 2x plus c. There's my answer. Okay. All right, here's our next problem, the integral of 4x squared over 49 plus 4x to the sixth. Again, you guys want to try a normal u sub. If I let u equal the denominator, my du will have an x to the fifth in it. I don't have an x to the fifth, so I'm going to try this as an inverse trig form. All right, and as an inverse trig form, I need to have the sum or difference of squares in my denominator. So I would have a 7 squared plus a 2x cubed squared. Okay. And like I said before, whatever's in here is going to be my u for my u sub. So if I let u equal 2x cubed, my du would be 6x squared dx. Okay, and however you want to deal with that change in coefficient, if I multiply by 2/3, I will get my 4x squared. So if I have 2/3 du, that'll give me 4x squared dx. Okay, so making that substitution, I'm going to have the integral of, in the denominator I have 7 squared plus u squared. Okay, in my numerator my 4x squared becomes a 2/3 du. So I need a 1 as a placeholder. So that 2/3 is a coefficient that's going to hang out front. Okay, this is an inverse tangent form, and with inverse tangent we have to be careful that we do 1 over a inverse tangent x over a. So a in this case is 7, because I have a 7 squared to get that 49. So I have 1 over a, or 1 over 7, inverse tangent of x over a, or u over 7 in this case. And then I'm going to plug back in for u. Let me simplify this a little bit. I have 2/3 times 1/7. That'll be 2/21. Inverse tangent of u is really 2x cubed, so 2x cubed over 7. And I need a plus c. And there's my completely ugly, but absolutely wonderful nonetheless answer. Okay, last one. I have the integral of e to the x over the square root of 16 minus e to the 2x dx. Okay, and again, if I try a normal u sub on this, and I have a u that has an e to the 2x in it, my du will also have an e to the 2x in it. And if that's the case, I'm not going to be able to do a traditional u sub, so I'm going to look at this as inverse trig. And again, it's important when you're doing inverse trig is to look at the denominator as the sum or difference of squares. So right now I have a 4 squared minus, what can I square to get e to the 2x? I square e to the x. Okay, and then I have that e to the x in the numerator. Just like I said before, whatever's in here, that's what I'm going to be using as u for my u sub. So u is e to the x, du is e to the x dx, and now my u sub is successful by looking at this as an inverse trig form. Okay. Sorry, that equal sign looks a little sloppy. So I'm going to make that u substitution. I'm going to have the integral of, in the denominator, I have square root of 4 squared minus u squared. Okay. My e to the x dx is a du. I need a 1 as a placeholder. Because I have that square root, it's an inverse sine form. So I'm going to have inverse sine of x over a, or u over 4. And then I plug back in for u, so I have inverse sine of e to the x over 4. plus c. Okay, so I feel like we covered a variety of examples, and we'll get more practice with this in class tomorrow.